All right, this is a continuation of notes for section 3.4. I had asked that you review the last example we did yesterday because it does apply to what we're doing today. So when we use that change of base formula, what did we do to the log base 1/2 of 2? How do we rewrite it? Okay, so log of 2 on top. What's on the bottom? Okay, it becomes log of 1/2, which if we expand that out is log of 1 minus log of 2. Yes? But what's the log of 1? Log of 1 is 0. So this becomes log of 2 over negative log 2. Yes? What I wanted you to notice is when you have the log of a fraction, like the log of 1/2, it really turns into negative log of 2. Okay? So the log base, if your base was, say, 1/3, you could rewrite that as what? Negative log 3. Okay, so we're going to look at that conversion today. We're going to start with a few graphs. It says using the change of base formula, we can rewrite any logarithmic function. So it doesn't matter what the base is, but we can convert it to a natural base. Okay, so log base b of x can be written as the natural log of x over the natural log of b. Right, your base goes in the basement. Okay, and then the natural log of b is just going to be a constant number. Whatever that base is, you can find the log of it. Okay, so we can factor that out front and think of it as 1 over the natural log of b times the natural log of x. Okay, so it says therefore every logarithmic function is really a constant multiple of a natural log. We can take any base and we can rewrite it as a constant times a natural log. Okay? All right, if the base is bigger than 1, the graph is going to have, thank you, the graph is going to be log base b of x with a vertical stretch or shrink. So remember that constant that we see in front, that 1 over natural log of b? It's going to come out to be a decimal most of the time. Okay? If that decimal number is bigger than 1, it's going to be a vertical stretch. If that decimal is between 0 and 1, it's going to be a vertical shrink. Yes? Okay. If it was something between 0 and 1, like we had in this example, right, where it was like a 1/2 or 1/3, it ends up being a negative in front. And what does a negative in front do to my graph? Reflects it over x. All right, so we might have an x-axis reflection as well. Come on. My board's off again. All right, here we go. So it says describe how to transform the graph of f of x equals the natural log of x into the graph of the given function. State the graph or sketch the graph by hand and support your answer with a calculator. So it's log base 5 of x. We can use a change of base, and instead of using base 5, we can use a natural log, which is what they've asked us to start with. Okay, so I can rewrite this as the natural log of x over the natural log of 5, just using that change of base formula. Okay, and then can we pull that natural log of 5 out front as 1 over? So it becomes 1 over the natural log of 5 times the natural log of x. Then grab your calculators. Let's figure out what is 1 divided by the natural log of 5. You will get a decimal. Anybody got it? 0.621 times the natural log of x is what it turns into. So if we already knew what the natural log of x graph looked like, What is the 0.621 in the front going to do? It's going to shrink it. Okay, so we have a vertical shrink of 0.621. All right, so let's go ahead and graph the natural log of x. When you're graphing logs, remember we rewrite them exponentially. So this would be the same as saying e to the y equals x. Yes? All right, let's make a t-chart for that. Picking our y's, let's just do 0, 1, and 2. E to the 0, 1. E to the first power, e to the first power, 2.7 roughly. Okay, e squared. What's e squared? Type it in your calculator, e squared. Okay, so about 7.4. Okay, so go ahead and plot those points. Looks like a normal log graph. Where would the asymptote be? At x equals 0? Okay, so what do we have to do to these points? Shrink them. All right. When we do a vertical shrink, we are shrinking the y values. Okay, so our y value on this first left dot here is 0. 0 times 0.621 is still 0. Yes? What do we get for our next dot? It was at a 1. It's going down to 0.621, about 0.6. Okay. And the other one was at a height of 2. What's 2 times 0.621? Okay. So our log graph is just a normal log curve. It's just been shrunk a little bit. All right. This next one, we have the log base 1/4 of x. What's another way we could rewrite that? Okay, so if we rewrite this using a natural log, this is the natural log of x over the natural log of 1/4. But that just becomes what? On the bottom there. Negative natural log of 4? Yes? All right, so our constant that would be in front is going to be 1 over the negative natural log of 4 times the natural log of x. So what would this do? This constant in front. 1 over negative natural log of 4. The negative is going to do what? Reflect over x. So we're going to, instead of having a log growth, it's going to look like log decay. Okay. And then what's the 1 over natural log of 4? What decimal? Did you do 1 over it?
Oh, no.
Okay. 1 divided by the natural log of 4. Okay. So we have another vertical shrink, since we're getting a number smaller than 1. But we're also going to have a reflection. So we're going to take our same points. We had 1, 0, 2.71, and 7.42. Okay. We're going to reflect them over the x-axis, and we're going to shrink them down a little bit. Yes? Does my first dot on the left change? If it was at 0 and I reflect it over x, doesn't move. If I multiply it by something, it doesn't move. So this point is still here. This one was up at 1. I reflected over x. It's now at -1. And now I'm going to multiply it by 0.7. So we're at -0.7. And this one was at 2. I reflected over. It's now at -2 times it by 0.7 roughly. We're at about -1.4. So we end up with that log decay looking curve. Okay? So really any base, the log using any base, could be converted into some kind of vertical stretch or shrink or reflection of a natural log curve. All right. So if you have a base that's a fraction, be something between 0 and 1, we can rewrite that as negative log of b, log base b. So you don't often see a base that's between 0 and 1. They're usually converted and just put the negative out front. Okay. This is just a review of your log graph, the basic shape of it. 2 key points. When we start doing all these transformations, I usually like to have 3 points that you move to really get an idea of how that curve is happening. But these are 2 easy points to graph, right? The log of 1 is 0. The log of your base is 1. So 1, 0, and B1 are always going to be points that you can use. And then I would just find a third point to make sure you're getting the curve correct. Okay. So at your tables, discuss what kind of transformations are happening in this first one. All right, I heard reflect over x, agree? And I heard left 1? Okay, so if it's reflected over x and it says log base 3, what was it originally? What was the base originally? It was a 1/3 base, right? They just converted it, okay? It's easier to make a t-chart when your base is a 3 versus a 1/3. All right, so if we're reflecting over x and shifting it left 1, where would our new asymptote be? Okay, and make sure you're giving me an equation, x equals -1. Whoops. All right. Let's go ahead and think about our parent function. If we ignore the reflection and the left 1, what was the basic function that we had? Y equals log base 3 of x. All right. Y equals log base 3 of x. If we write that exponentially, we are saying 3 to the y equals x. So what kind of values could I plug in? If I use a 0, I get 1. If I use a 1, I get 3. And if I use a 2 for my power? All right. So remember on that graph we just talked about, the point 1, 0 is on my graph, and the point B1, 3, 1 in this case, is on my graph. And we just found that third point. So go ahead and plot those. And now we want to reflect them over x and shift them left 1. All right, so we end up with that log decay shape? Yes? All right. Where do we have a y-intercept? It ended up at 0 at the origin? Okay, let's check to see if that's right. If we put a 0 in here for x, we're really saying y equals negative log base 3 of 1. But 3 to what power gives you a 1? 0. And negative 0 is 0. Okay. Domain? Okay. Do we include the negative 1? No. All right. Range? All reals. Negative infinity to infinity. And how about end behavior? Remember, you only have to list one. Which way are we going? Towards positive infinity? Okay. So the limit of f of x as x goes towards positive infinity is negative infinity. Yep, we're heading down there. Okay. All right. The second graph that we're going to look at, we are going to rewrite this equation getting rid of a fraction base. Okay. So instead of a base of 1/2, what could we do to this equation? We can change it to what base? A 2. Instead of a 1/2, we can use a base of 2 if we change what? Instead of a plus sign here, we have a minus sign. So we're going to think of this as negative log base 2 of the 3 minus x. But what did we have to always do to that 3 minus x piece? Flip it around. Okay. Pull the negative out, right? And it's going to be x minus 3 inside. And then this 2 that was in the very front piece is really what we usually have on the end, our vertical shift. Okay. So at your tables, discuss the transformations. All right, I heard reflect over x and y. Yep. Agree? And then what? Okay, so let's start with our basic points. Log base 2, so we're looking at the equation 2 to the y equals x for our t-chart. We okay with that? All right, 0, 1, and 2 gives me 1, 2, and 4. All right, plot the points. All right, asymptote moves to where? Okay, for shifting right 3, we're going to move that asymptote over here. All right, so we have to take those 3 dots, reflect them over x, reflect them over y, right 3, and up 2. All right, I'm going to pause the video. You guys go ahead and move the points. Okay, let's check your points. You should have a dot at negative 1, 0. You should have one at 1, 1 and at 2, 2. Yes? So this becomes a reflected curve. Yes? So, domain? Okay. Range is everything. Which way is our limit going to go? Limit as x approaches, we're going to the left towards negative infinity. Okay. So the limit of my function as x approaches negative infinity is negative infinity. All right, the only thing we didn't check is the y-intercept. If we put a 0 in for x, okay, putting a 0 in for x, inside all this parentheses stuff turns into what? Just a 3. So we have y equals negative log base 2 of 3 plus 2. So grab your calculators. If you have the newer calculator, you should be able to just tell it to use a base of 2. If you don't, think of that change of base and just do log 3 divided by log 2. What do we get? Okay. Does that fit what our graph is saying? Did we intercept at about 0.4? Yes? Okay. The last two on this page, we are just identifying the domain. And we did some almost identical to this a couple days ago. What was the restriction when you're taking a log? You're only allowed to take logs of what? Positive numbers. All right, so that means whatever's in parentheses here, which in the first one would be an x squared minus 16, it has to be positive. Okay? So that means x squared has to be bigger than 16. Well, what kind of numbers can we square and get something bigger than 16? Anything over 4 or less than negative 4, right? On the outsides. If we think of the graph of x squared minus 16, it's just a parabola that's been shifted down 16, right? And it's going to intersect the x-axis at 4 and negative 4. So if we want to be positive, we want to be in the two parts that are above the x-axis, then we have to be on the outsides. So something over here or something over here. So my domain would be from negative infinity to negative 4, and then jumping over and going from 4 to infinity. Do I include the 4 in the negative 4? No, because I can't equal it. I have to be strictly greater than it. Okay? At your tables, go ahead and discuss question B. Okay, at your tables, you should have hopefully focused on the 4 minus the square root of x piece. And it has to be what? Greater than 0. If we add the square root of x part to the other side, we're saying 4 is greater than the square root of x. So what kind of numbers could we put in for x that would give me exactly 4? 16. Square root of 16 would give me a 4. We need to be smaller than that, right? Because if we put in, for example, the square root of 25, now this is negative. Okay? So we need numbers that are smaller than 16. But there's another restriction. Because it's a square root, we can't square root negatives, which means my x can't go past 0. All right, so I have to be 0 or higher, but staying under 16. All right, so my domain would look like this. Okay? All right. If we are seeking a model, for a set of data, it is often helpful to transform the data by applying a function to one or both of the variables in the data set. This we did already when we treated a year, like if we were going from 1900 to 2000, we rewrote it thinking of it as 0 to 100. So we would have said a statement in there, let x equal the number of years after 1900. Okay? That process is called re-expressing the data. So we're going to look at an example of where we could re-express some data. Back in chapter 2, we had an example or two involving Kepler's third law. It says, remember that it is the square of the orbit period t for each planet is proportional to the cube of its average distance a from the sun. So the square of the time it takes to make an orbit is proportional to the cube of the distance from the sun. If we re-express that data using Earth-based units, what is our calendar year? How many days? Okay, so what we can do is we can re-express the data using Earth's orbit, right, the time for an orbit, and Earth's distance from the sun. So we're going to take all of the data that we had back in chapter 2, and we're going to divide the orbit by 365.2. We're going to divide the distances by 149.6, and we get this new set of data. What happened to Earth? Look at your chart. What ends up happening for Earth? If we take Earth's orbit time and divide by 365.2, we get 1. If we take Earth's distance from sun and divide by the distance to the sun, we get 1. So by re-expressing our data, we are getting a coordinate for Earth of being 1, 1. Okay? It's just a more convenient value. All right? If you graph the original data from chapter 2 and this new re-expressed data, they look almost identical. Okay, so the left picture was the graph from chapter 2, the right picture is our graph now. So we're really just saying we want to make this more convenient. We want to have a point that's easy to identify. All right, so the point 1, 1 becomes Earth on that set of data. All right, so what we're going to do is we're going to look at how we can use that data to develop Kepler's law. And I flipped too fast here. All right, so I need you to enter the distance from the sun as your list 1 and the period of orbit as list 2. Okay, so you've entered the distance as list 1 and the time of orbit as list 2. Example 7 says we are going to re-express that data. Okay, so A was list 1, T was list 2. We are going to re-express it using natural log of A and natural log of T. Now you don't have to take each point in there and find its log and type that in. So go back to your calculator, go over to list 3 and arrow up so where it says L3 you've got that highlighted. Okay? We're going to tell it to use a formula. We want it to take all the data from list 1 and take its natural log. So we're going to type in natural log and then second 1 will get us list 1. And when I hit enter, it's going to use that formula to create my list 3. Okay? And you can do that with any formula. Let's say you just wanted to add 2 to every data point. You could say take list 1 plus 2 and it would fill your whole column in. Okay? Go over to list 4, arrow up, and this time we want the natural log of list 2. Okay. It says to find a linear regression model. When we graphed the original data that was in our chart, our list 1 and 2, it had a curve to it, yes? It looked more like an exponential growth kind of situation. If we graph list 3 and 4, it's going to be linear or close to it. So we want to do a linear regression with list 3 and 4. We're not going to bother graphing it, so you don't have to worry about storing it anywhere. So let's go to StatCalc number 4, linear regression. Tell it to use list 3 and list 4. All right. So I'm getting an equation, y equals 1.499x plus 0.000695. Notice that your b term is in scientific notation. Okay. Let's do some rounding. 1.4995 is close to 1.5. So let's think of this just as y equals 1.5x. And the number 0.000695, 0.000695 is very small, yes? So our y-intercept is almost 0. So we're going to simplify this equation down a little bit. We're just going to think of it as y equals 1.5x. Our y's came from list 4, right? And list 4 was the natural log of what? List 4 was the natural log of t. So my y value is really the natural log of t. And my x value is really the natural log of a. All right. Now it says rewrite your linear regression in terms of a and t, which we did. And now rewrite the equation in a form that has no logs and no fractional exponents. Could we divide the natural log of a to the left side? So it's going to look like the natural log of t divided by the natural log of a equals 1.5. But the natural log of t divided by the natural log of a, that's just that change of base formula, right? You have the log of the big number over the log of your base. So this could be written as the log of t using a base of a. That's just that change of base idea. Okay. Now, if we want to write this without having any logs in it, can we write it exponentially instead? Do our little circle thing. So we're saying a to the 1.5. Can I write that as a to the 3/2? Is that the same thing? Equals t. But then it said we don't want any fractional exponents. What does that little 2 in the denominator of our power mean? It's a square root. So could we square both sides to get rid of that? If we square both sides, we've got a to the 3rd equaling t to the 2nd. And that's Kepler's third law, right? It said it was the cube of the distance equaling the square of the period for its orbit. All right, we're going to do one more quick. It's another log equation. We aren't going to have to re-express anything here. We're just looking at how we can use this equation. It says we have this law of forgetting that states that if a task is learned at a performance level p sub 0, then after a time interval of t, the performance level p satisfies that equation. I'll give you an example. You study for a test. You take the test today and say you get 95%. What's going to happen if you take that test a year later and you don't restudy for it? You're not going to get the same score, right? Your score is going to go down. All right, so for our example here, it says that C is a constant that depends on the type of task, and T is measured in months. And they're asking us to solve this for P. If you look at the right-hand side, you have an expanded log statement. Can we condense that? Think about what we did yesterday. Can we condense that back so it's just one log? What would the C do? Goes back as a power, okay? So we've got the log of P equals the log of P sub 0 minus the log of T plus 1 to the C power. Okay, we put that back as a power. What does the minus condense back to? Okay, so we've got the log of P equals the log of P sub 0 divided by T plus 1 quantity raised to the C power. And if you have the log of something on one side equaling the log of something on the other side, those two somethings have to match. Okay? In other words, the log of 2 can't equal the log of 3. So that means that P has to equal, P has to equal P sub 0 divided by T plus 1 quantity to the C power. Yes? All right. So for this example, it is a test situation. It says we scored a 90% on a math test. What would our score be after 2 months and after 1 year? It says assume that your C value is 0.2. So after 2 months, our T value is 2. After a year, our T value is 12, since we're talking months. What was our initial value? 90 is P sub 0, our initial score. So we have the equation P equals 90 divided by 2 plus 1 to the C power. And they gave us a C value of 0.2. So we need 90 divided by 3 to the 0.2 power. What do we get? Go ahead and round it to a whole number since it's a test score. What are we getting? 72? Okay. So after 2 months, our score would have gone down from 90 to 72. What about after 12 months? Now we have 12 plus 1 to the 0.2 power as the denominator. So what's 90 divided by 13 to the 0.2? Okay, so now our test score a year later, if we hadn't restudied, would be down to a 54%. Okay. All right, there's your assignment. I'll get you some graph paper.